Hello and welcome to Astronomy 101 at Mount San Jacinto College. I am Professor Lee and I will be your instructor for this class. I was an experimental condensed matter physicist when I went to school and may end up going through this class from a physicist's perspective, but as is evident if you look at my introductory videos for other classes, I have found that the story of astronomy and its discoveries laid the groundwork for physics and other sciences. The study of stars, planets, and other celestial bodies built up our understanding of the universe around us from time immemorial and continues to do so as we develop telescopes which allow us to see the first galaxies which formed 13.5 billion years ago and to detect ripples in space-time called gravitational waves for the first time. We have cataloged over 3,700 planets orbiting nearby stars, and Voyager 1 became the first man-made object to leave the solar system, possibly second after a manhole cover which achieves escape velocity after a sewer explosion, but the first that we know of, definitely. We are learning about the past and charting a course to the future. To begin this journey, we start with Chapter 1, Discovering the Night Sky, where we will learn some of the tools to begin looking at the sky above and around us as astronomers, and go over how our motion through the cosmos helps determine some of the most basic characteristics of life on Earth. The first thing I want to present this brief overview of the history of astronomy, which we will cover in more detail moving through the book. Beginning in 2136 BCE, when Chinese astronomers recorded a solar eclipse, and moving through the present day, where we are actually beginning to travel beyond the boundaries of Earth. I will leave you to go through it in the book on your own because, as I said, we will be exploring it in much more detail throughout the class, but I would like to mention two things. The first thing I would like to note is that despite starting with the Chinese observations, the history is slightly Eurocentric as it goes from the Greek Golden Age to the European Enlightenment period. But curiosity and observation are general human characteristics, and societies across the globe have recorded the movements of the stars, such as the Mayans, who famously made calendars with more accurate days and years, quantities which depend on Earth's movement around its axis and around the sun, respectively, and then the Greeks, and Islamic scholars whose doubts on the Greek/Egyptian Ptolemaic geo or Earth-centric model of the universe influenced Copernicus in his helio or sun-centered model. I would also like to note the large scale time between 2136 BCE and 1543 CE, when Copernicus published his De Revolutionibus Orbium Coelestium on the revolutions of the celestial spheres, which kickstarted our modern understanding of astronomy. Part of this is due to Eurocentrism, as I have said, but a much more interesting implication to it is that we have been learning astronomy since time immemorial, and have only just began to scratch the surface in the past 500 years, and there's still work to be done. The universe is big. The size of the observable universe is about 10 to the power of 41 times the size of a proton. It is also interesting to note that the size of the human body compared to a proton is about the size of the universe compared to the human body. Because of these differences in scale, physics tends to be broken up into subfields based on what size of what you're looking at, with particle physics looking at very small things such as a proton, a size of about 10 to the negative 15th meters, biophysics looking at things the size of a virus, about 10 to the negative 6 meters, classical physics looking at things about the size of a human, 10 to the 0 or 1 meter. I'm about 1.8 meters tall, so a meter is a good scale for the world immediately around us. And condensed matter physics looking at things ranging from about 10 to the negative 6 to 1 meter. Astronomy is the study of everything bigger than this and ranges in scale from the diameter of the Earth, about 10 to the 7th meters, to the size of the observable universe, about 10 to the 26 meters. Still, we can't totally neglect the physics of smaller things, as astronomy was instrumental in discovering the physics from the theory of gravity, which pulls the Earth to the Sun and us to the Earth, to quantum mechanics, which arose from studying the electromagnetic radiation of the Sun and determines the properties of the smallest particles in the universe. Because astronomy relies on things that are so much bigger and smaller than each other, it is useful to use a logarithmic scale similar to the Richter scale, which is based on how many magnitudes of 10 bigger something is than another thing. For example, the distance from the Earth to the Sun is about 10,000 times the diameter of the Earth, but the distance from the Sun to nearby stars is about 100,000 times bigger than this, or 1 billion times the size of the Earth. These numbers can get out of hand quickly, so we introduce a logarithmic or power scale where we say that the distance from the Earth to the Sun is 10 to the fourth, a 1 with 4 zeros after it, times the diameter of the Earth, and the distance to the nearest stars is 10 to the ninth, a 1 with 9 zeros after it, the diameter of the Earth. You probably already know an example of logarithmic scales with centimeters and kilometers. 1 kilometer is equal to 10 to the third meters, where the meter is the SI unit or International System Unit for the length of something, and a unit is a word which we use for something which can be measured or calculated, such as length, which has units of meters, or time, which has units of seconds. And 1 centimeter is equal to 10 to the negative 2 centimeters. The centimeter and kilometer are useful for different length scales and are related to each other by the kilometer being 1,000 meters and a meter being 100 centimeters. So 1 kilometer is equal to 100,000 centimeters. To write out very large or small numbers, we then use scientific notation where we keep the significant digits, everything between the first and last non-zero digits, with 1 to the left of the decimal point and multiply by the magnitude powers of 10. For example, 55,000 is 5.5 times 10,000, which is 5.5 times 10 to the fourth. You can find magnitude for a number greater than 1 by counting the number of digits between the right of the first significant digit and the decimal place, in this case 4. For a number less than 1, count the number of digits from the decimal place to the right of the first significant digit and put a negative sign there. For example, 0.0172 has 2 digits from the decimal place to between the 1 and 7, with the 1 being the first significant digit, and is therefore 1.72 times 10 to the negative 2, or 1.72 times 1 over 10 to the 2, or 1 over 100. A negative exponent means you divide by 100 rather than multiply by 100. Now that we are properly equipped to talk about the scale of the universe, let's talk about how it appears to us with our naked eye. We can see about 6,000 stars over the entire sky without the aid of telescope, or 3,000 stars at a single time because half of them are hidden under the horizon. As you probably know, these stars form patterns which are called constellations. What you might not know is that each collection of stars is technically called an asterism, shown on the left, while the area of the sky which encloses them is the constellation, but these terms can be used interchangeably. There is nothing which actually connects the stars in a constellation to each other than their position in the sky. Stars might look to be right next to each other from our perspective, but one can actually be much farther away than the other. However, recognizing these patterns allows us to identify which stars are which, and further to recognize other constellations and their constituent stars using constellations which are easy to find, such as the Big Dipper. In the diagram on the left, we see how we can use pointer stars in the Big Dipper to find Polaris in the Little Dipper, called the North Star, because if you face it, you will always be facing north, by following the line between the two stars on the edge of the Dipper's basin. By following the pointer stars on the other edge of the basin, you can find the star Regulus in the constellation Leo, and by following the arc of the Dipper's handle, you can find the stars Arcturus and Spica in the constellation Bootes and Virgo. Similarly, and all of this is assuming you are in the northern hemisphere, by the way, 3 of the brightest stars in the winter sky, Procyon, Betelgeuse, and Sirius, and Orion, Canis Minor, and Canis Major, are called the winter triangle and allow you to identify these constellations. Similarly, there is a summer triangle connecting the constellations Cygnus, Aquila, and Lyra. Astronomers require more accuracy in locating dim objects than is possible simply by moving from asterism to asterism. They have therefore created a sky map on a surface called the celestial sphere and applied a coordinate system to it, analogous to the coordinate system of north-south latitude and east-west longitude imprinted on globes of Earth. If you look at the sky year after year, you will see that the stars do indeed appear fixed relative to one another. Furthermore, throughout each night, the pattern of stars appears to rigidly orbit Earth. We employed this artificial Earth-based view of the heavens to make celestial maps by pretending that the stars are attached to the inside of an enormous hollow shell, the celestial sphere, with Earth at its center. Using the celestial equator and poles as reference features, astronomers divide up the surface of the celestial sphere in precisely the same way that the fixed latitude and longitude grid divides Earth. The equivalent to latitude on Earth is called declination on the celestial sphere. Fixed on the celestial sphere is measured from north to south of the celestial equator. The equivalent of longitude on Earth is called right ascension on the celestial sphere, measured from 0 hours to 24 hours, where hours denotes hours, the units of angular measurement for right ascension, around the celestial equator. The boundaries of the constellation introduced above run along lines of constant right ascension and constant declination. Because stars are all so far away, the right ascension and declination does not change perceptibly over our lifetimes, except as measured in modern observatories which can detect changes for some of the nearer ones. The alt-azimuth system depends on your location. It is easy to use. First, find the North Pole star, Polaris. Facing the direction of Polaris, you are facing due north. Look straight up at the horizon below Polaris. This is the alt-azimuth system. Altitude is the angle straight up from the horizon towards your zenith, the point directly overhead. Every place has a different zenith. Altitude runs between the horizon and at the zenith. The angle to the right of north along the horizon is the azimuth coordinate in your position. We have defined the celestial sphere, which has poles and an equator like Earth's, and two coordinate systems through which to locate objects in the sky. These coordinate systems differ as the stars seem to move with respect to the Earth, if not each other, as the night passes and one keeps the stars fixed on the celestial sphere, while the altitude and azimuth are continually changing. However, as time passes, the objects in the solar system do seem to move. The word planet actually comes from the Greek word for wanderer, which means that they have no fixed coordinates. The Earth orbits the Sun in a plane called the ecliptic, but because of the 23.5-degree tilt between the Earth's axis of rotation and the ecliptic, the Sun appears to orbit the Earth at an angle where the position of the Sun on the celestial sphere appears to be orbiting in a loop at this angle with regards to the celestial equator. Because of this tilt, the two loops meet in two places. Where the Sun is heading northward, this intersection is called the vernal equinox. Halfway around the two circles, they meet again at the autumnal equinox. At this time, the Sun is heading southward. Just as the location of Greenwich, England defines the prime meridian or zero of longitude on Earth, we need to establish a zero of right ascension. This zero value is defined at the vernal equinox. When talking about the celestial sphere, we suppose that each star and planet is the same distance away and glued to the inner surface of the sphere some distance away from Earth. This is not true, but is consistent with what it looks like from our personal perspectives. A side effect of this is that objects in the sky that are very far away in reality, such as the stars, can look much smaller than objects which are in reality smaller but closer, such as the moon. Because of this, we talk about the arc angle, generally just called an angle, which is covered by an object rather than the physical diameter of an object. The diagram on the lower right demonstrates that when we look at the moon, about 1/720th of a circle surrounding us is covered, but its physical diameter, which means that since there are 360 degrees in a circle, about 1/720th times 360 degrees, or 1/2 of a degree, is covered by the moon. You can also see on the upper right a weird quirk of the solar system, which is that although the moon is much smaller than the sun, they cover about the same amount of the sky because the sun is much farther away, about 1/2 degree. Humans are infamously bad at measuring angles by eye, so some tricks for estimating the angle subtended or covered by an object in space is to hold your hand out at arm's length and know that the width of your index finger is about 1.5 degrees and the distance between the tip of your index finger to the first knuckle is about 2 degrees, from the first to second knuckle about 3 degrees, and from the second to third about 6 degrees. You can also convert from this angular diameter to a physical diameter if you know how far away something is by remembering that for a right triangle, the opposite side, physical radius of the object, where the radius is half the diameter of an object, or the distance away from the center to one side rather than from one side to another, over the adjacent side, how far away the object is equal to the tangent of the angle, the angular radius. From this, we make a small approximation, which is very good for small angles, that the tangent of the angular diameter is equal to the physical diameter over the distance. Put another way, physical diameter is equal to distance times the tangent of angular diameter. Having talked about ways to understand and measure our night sky, we now move on to the effects that the motion of the Earth through the solar system and about its axis affect our day-to-day life. The daily and annual rhythms of the sky, Earth, and all life arise from three celestial motions. Earth's spinning, which causes day and night, as well as causing the apparent daily motion of the celestial sphere and all the objects on it. Earth's orbit around the sun, which creates the seasons, the year, the change in times and locations of sunrise and sunset, as well as which constellations are up at night. And the moon's orbit around Earth, which creates the lunar phases, the cyclotides, and spectacular phenomena we call eclipses. As discussed in Chapter 2, the moon does not actually orbit Earth. Rather, the moon and Earth waltz together around a common point called the barycenter, located about 4670 kilometers, or 2,900 miles, from the center of Earth in a straight line between the centers of the two bodies. For convenience, we will continue to use the shorthand that the moon orbits the Earth throughout this chapter and expand on the concept of barycenter in Chapter 2. This is also true of the motion of planets around the Sun, but it's less noticeable as the Sun is much more massive than the planets, and the barycenter ends up being very close to the center of the Sun. But the small wobbling induced in stars by their waltz with large planets is one of the tools which allows us to find exoplanets or planets orbiting their stars. Rotation creates diurnal or daily motion. Earth's rotation is counterclockwise as seen from above our North Pole. That motion causes the stars as well as the sun, the moon, and the planets to appear to rise along the eastern horizon, move across the sky, and set along the western horizon. Revolution creates our year. The length of any cycle of motion measured with respect to the stars is called a sidereal period. So Earth's sidereal period is 365 and 1/4 days long. Earth also has a sidereal day. Due to Earth's rotation, every star outside the solar system rises and sets in a 23-hour, 46-minute, and 4-second cycle, one sidereal day. However, we don't see the same stars every night throughout the year because of Earth's motion around the star. That motion delays when the sun will rise by 4 minutes compared to the preceding day, which is why our normal clock time is 24 hours long. This is called a solar day. Using this diagram, we can easily see the difference between the sidereal and solar days, as it takes 23 hours, 56 minutes for the Earth to rotate 360 degrees, but by the time it has done that, Earth has revolved slightly around the sun, and the section of the surface which was pointing towards the sun is now pointing into space. The Earth has to rotate ever so slightly more for that section of the surface to again be pointing directly towards the sun, which accounts for the longer length of the solar versus sidereal day. When we talk about the sun or the moon or a planet being in a zodiac sign, we are talking about said celestial body literally being in the section of the sky determined by said zodiac sign's constellation. Most of the planets in the solar system are within a few degrees of the ecliptic. The biggest deviation is Mercury, which is 7 degrees off. This means that while there may be 88 constellations making up the sky, the motions of the planet, moon, which is about 5 degrees off the ecliptic, and sun only pass through the 13 constellations that the ecliptic journeys through. These are called the zodiac constellations and contain the 12 you probably know about from astronomy and Ophiuchus. Because there are actually 13 constellations, not all of the same width, the sun's passage through each does not actually align very well with the monthly patterns of astrology. For example, I was born in October, which makes me a Libra, but the sun was actually in Virgo at this time. As briefly noted when talking about the two types of coordinate systems, while the stars do not move relative to each other over the course of the night, they do move around the sky because of the rotational motion of the Earth. Stars and constellations that never go below the horizon as seen from a north pole are circumpolar and will rotate around Polaris, the North Star. While there is no bright South Pole star equivalent to Polaris, all stars seen from the South Pole are also circumpolar and move from right to left. Looking at the pictures on top, we can see this motion of the circles that the stars trace out through the night. There are stars that do not go below the celestial equator or horizon as their spins. If you live in the northern hemisphere, Polaris is always located above your northern horizon at an angle equal to your latitude. Only the stars and constellations that pass between Polaris and the land directly below it are circumpolar. Because Earth rotates around the axis through its poles, stars seen from these locations appear to move in horizontal circles. Standing on the equator, you are perpendicular to the axis around which Earth rotates. As seen from there, the stars rise straight up on the eastern horizon and set straight down on the western horizon. Seasons are a result of the tilt of the Earth with respect to the ecliptic. The amount of time the sun spends in the sky per day depends on how high it is in the celestial sphere. For the northern hemisphere, this time is minimized during the winter solstice, where the sun is farthest below the celestial equator, and maximized during the summer solstice, where the sun is highest above the celestial equator. The points where the ecliptic intersects with the celestial equator are called equinoxes, vernal and autumnal, where the sun is in the sky for exactly half the day, thus equinox or equal night. Additionally, because the differing angles that the sun makes with the celestial sphere, the sun's maximum angle above the horizon is lower, which means that the projection of its light along the ground is more spread out while it is higher in the summer, and the projection of light along the ground is more concentrated. Try holding a flashlight at different angles above paper and seeing how diffuse/concentrated the beam is on the paper as a function of the angle. On the winter solstice, the first day of winter, the sun rises south of east, is lowest in the noontime sky, stays up the shortest time, and its light and heat are least intense, most spread out of any day of the year in the northern hemisphere. On the vernal equinox, the first day of spring, the sun rises precisely in the east and sets precisely in the west. Its light and heat have been growing more intense, as shown by a smaller, brighter oval of light than in the first diagram. On the summer solstice, the first day of summer, the sun rises farthest north of the east of any day and highest of the noontime sky and stays up for the longest time, and its light and heat are more intense than on any day of the vernal in the northern hemisphere. On the autumnal equinox, the same astronomical conditions exist as on the vernal equinox. The temperature and hence the seasons are determined by the duration of daylight at any place and the height of the sun in the sky there. The motion of Earth around the sun and its spinning on its axis determines the properties of the year and the day, but there are wobbles. While noon is traditionally seen as the time when the sun is at its highest point in the sky, Earth's rotation axis is rotated 23.5 degrees from being perpendicular to the ecliptic. Our planet's speed along the ecliptic increases as we approach the sun, and it decreases as we move away from it. This change in Earth's speed throughout the year has the effect of moving the sun across the sky at different rates, thereby changing the time when it is highest in our sky, as seen on the diagram to the left, where the clock and astronomical noontime can be off by as much as 16 minutes from its average. Additionally, the sun is highest in the point at different times for different longitudes, as this is determined by when the surface you are at is pointed directly at the sun. Even if we use an average astrological noontime as our clock noontime, for every mile you drive east or west, the astrological noontime shifts ever so slightly. To deal with this, we created time zones which set a noontime for 1/24th of the globe each and shifted the noontime by an hour every time you cross one of these lines. Good enough. There's also an issue of in that the year is defined by the revolution of the Earth around the Sun and the day by the revolution of the Earth around its axis. These are not related to each other, and one does not fit into the other by an integer number. The year is, in fact, 365 days, 5 hours, 49 minutes, and 1.1 seconds, approximately. Julius Caesar accounted for this by introducing leap years in the Julian calendar, where an extra day was added every 4 years to prevent calendar from drifting from the actual astronomical solstices and equinoxes. But this system produces an error of about 3 days every 4 centuries. To solve this problem, Pope Gregory decreed that century years would be leap years only if evenly divisible by 4. For example, the years 1700, 1800, and 1900 were not leap years under the improved Gregorian system, but the year 2000, which can be divided evenly by 400, was a leap year. This still produces an error, but only an error of about 1 day every 3,300 years. This wonkiness with the calendar is also in place with the month. The calendar month is inspired by, but not beholden to, the lunar cycle. The sidereal month of the moon is the time it takes for the moon to start at one place on the celestial sphere and return to exactly the same place again, thereby completing one full orbit of Earth. In other words, the length of the sidereal month is determined by the location of the moon among the stars. The sidereal orbit period of the moon takes approximately 27.3 days. The synodic month, or lunar month, is the time it takes for the moon to complete one 29.5-day cycle of phases, for example, from new moon to new moon or from full moon to full moon, and thus is measured with respect to the sun rather than stars. This is pretty close to the average length of a month, 30.436875 days, but the amount of leap events needed to adjust the calendar month to a synodic month would be very unwieldy. It is still useful to keep track of our journey through time, as each synodic month is tracked through the phases of the moon each night. The sun illuminates half the moon at all times. The moon's phases that we see depend on how much of its sunlit hemisphere is facing Earth. When the moon is closest to the sun in the sky, its dark hemisphere faces Earth. This phase, during which the moon is at its most tiny crescent, is called a new moon. During the 7 days following the new phase, more of the moon's illuminated hemisphere becomes exposed to our view, resulting in a phase called the waxing crescent moon. At the end of this period, we see half of the illuminated hemisphere and half of the dark hemisphere. This is called the first quarter moon. Quarter moon refers to how far in its cycle the moon has gone, rather than the fraction of the moon which appears lit by sunlight. During the next week, still more of the illuminated hemisphere can be seen from Earth, giving us the phase called the waxing gibbous moon. Gibbous means rounded on both sides. Then the moon arrives at the opposite side of Earth from the sun, and we see virtually all of the fully illuminated hemisphere. This phase is the full moon. Over the following 2 weeks, we see less and less of the illuminated hemisphere as the moon continues along its orbit. In order of occurrence, the movement produces the phases called waning gibbous moon, the third quarter moon, and the waning crescent moon. Additionally, there is a difference between the dark side and the far side of the moon. As we can see in the diagram, half the moon is always lit by the sun, just as half the Earth is, and that side is always dark. However, through a quirk of fate, the period of rotation of the moon also means that it is always facing the Earth with the same face. This will change eventually, but not in our lifetimes. That means that the side of the moon, not the dark side, is always hidden from our view, and this is called the far side of the moon. As stated before, and as I assume you know, the Earth is spinning like a top about its axis. Looking at the middle diagram, if the top were not spinning, gravity would pull it over on its side, but when it is spinning, the combined actions of gravity and rotation cause the top's axis of rotation to precess or wobble in a circular path. The same is true for the Earth, which is slowly wobbling like a top as the sun and the moon's gravity pull it in the same way as Earth's gravity pulls the top. As with the toy top, the combination actions of gravity from the sun and moon, along with our planet's rotation, cause Earth's axis to trace a circle in the sky while remaining tilted about 23.5 degrees away from the ecliptic. It takes about 26,000 years to trace this circle, but this means that the North Star is changing over time. At the present time, Earth's north axis of rotation points within the 1 degree of the star of Polaris. In 3000 BCE, it pointed near Thuban in the constellation Draco, the dragon. In CE 14,000, the pole star will be near Vega in Lyra. Recall the intersections of the celestial equator and the ecliptic defined by the equinoxes. So these key locations in the sky shift slowly from year to year. This entire phenomenon is oftentimes called the precession of the equinoxes. To round out the lecture, we will explore some of the most spectacular phenomena to grace the sky: eclipses. An eclipse occurs either when the moon is fully passed between the sun and the earth and covers the sun and the sky, a solar eclipse, or when earth passes between the sun and moon and casts a shadow over the moon. It would be natural to assume that this occurs about once a month, but because its orbit is tilted from the ecliptic, the moon is usually above or below the planes of our orbit around the sun. The moon crosses the ecliptic at what is called the line of nodes, an eclipse taking place only when the moon crosses the plane of the ecliptic during its new or full phase. By calculating the number of times a new moon takes place on the line of nodes, we find that at least 2 and no more than 5 solar eclipses occur each year. Lunar eclipses occur about as frequently as solar eclipses. Each year has a minimum of 4 eclipses, solar plus lunar, with the maximum possible number of 7 eclipses, solar plus lunar. There are 3 types of lunar eclipses, and in order to understand them, we have to define the terms umbra and penumbra. The umbra is the part of the shadow where all direct sunlight is blocked by the Earth. If you were in Earth's umbra looking at Earth, you would not see the sun behind it at all. The penumbra of the shadow is where Earth blocks only some of the sunlight. If you were in Earth's penumbra looking at Earth, you would see a crescent sun behind it. The moon has an analogous umbra and penumbra. A penumbral eclipse, wherein the moon passes through only the Earth's penumbra, is easy to miss. The moon still looks full, just a little dimmer than usual, and sometimes slightly reddish in color. When just part of the lunar eclipse passes through the umbra, a bite seems to be taken out of the moon, and we see a partial eclipse. When the moon travels completely into the umbra, we see a total eclipse of the moon. Total lunar eclipses, with the maximum duration lasting for up to 1 hour and 47 minutes, occur when the moon is closest to Earth and is traveling directly through the center of the umbra. 3 types of solar eclipse also occur. When the moon completely covers the sun, the result is a total solar eclipse. You can see that only the tip of the moon's umbra ever reaches Earth's surface. As Earth turns and the moon orbits, the tip traces an eclipse path across our planet, as seen in the middle diagram. Only people within these areas are treated to the spectacle of a total solar eclipse. When only the penumbra sweeps across Earth's surface, as happens in high latitude regions, the sun is only partly covered by the moon. This circumstantial results in a partial eclipse of the sun. Similarly, people in the penumbra of a total eclipse see a partial eclipse. In either case, the sun looks crescent-shaped as seen from the Earth. The moon's orbit around Earth is oval-shaped, therefore the distance between the Earth and the moon, which averages about 384,400 kilometers or 238,900 miles, varies by 14% as the moon moves around the Earth. Consequently, the angular size of the moon in our sky varies by that amount. The width of the eclipse path depends primarily on the Earth-Moon distance during an eclipse. From Earth's surface, the moon then appears too small to cover the sun completely, and a thin ring or annulus of light is seen around the edge of the moon at mid-eclipse. This type of eclipse is called an annular eclipse. The length of the moon's umbra is nearly 5,000 kilometers shorter than the average distance between the Moon and Earth's surface. Thus, the Moon's shadow often fails to reach Earth, making annular solar eclipses slightly more common than total solar eclipses. Thank you for your time, and I look forward to a spectacular semester.